quick review about testing the mean of a population with a single sample. So what do we do? Step 1, set up the null hypothesis. So here we're going to state some statement about the mean of the population, and that is, in this case, we're saying it's a particular value, mu0. Then set up the complement of that, and that's the alternative hypothesis, in this case, the two-sided. Then step 3, choose an alpha level, and the ubiquitous alpha we can choose is 0.05. So let's just choose that one, for example. And then step 4 is to take a sample of size n and calculate either z or t. In either case, what we're doing is we're comparing the sample mean to the hypothesized population mean and seeing how far apart they are. In both cases, we're doing that. See how far apart x bar and mu naught are. So if they're very close together, then we'll say, oh, look, the data is consonant with our hypothesis. If they're far apart, then we're going to say, no, let's reject this null hypothesis because the data doesn't agree with it. So how do we judge what's small and what's big? Well, we divide by the standard deviation. We standardize. Divide by the standard deviation. We need the standard deviation of x bar, of course. And in this case, it's sigma over the square root of n. There it is, the standard error. Now, if we know sigma, then z has a normal distribution. On the other hand, if we don't know sigma, we can estimate it by s, and then we look at t. And t, this has a student's t distribution. If the population that we're looking at is approximately normal. Then what do we do? Well, we compare these values to our cutoffs. So, for example, we can calculate the appropriate p-value for those for our statistic, and then compare that p-value to alpha, and either reject h0 or not. If the p-value is less than alpha, we'll reject. If not, we won't reject h0. Alternatively, we can look at finding the cutoff. For example, if we were looking at the z, our cutoff would be plus or minus 1.96, and then compare our statistic, in this case the z, to plus or minus 1.96, or in the case of the t, whatever the appropriate cutoff is when we get the degrees of freedom, and then we reject h0 or not. So in either case, we're going to come up with either reject the hypothesis or not. Now, let's move on and let's generalize this to the situation where we have two samples. So the two sample situation, why would we look at this? Well, one example might be if we have a before and after situation. So you've seen those ads where you see the person before going on the diet and then after going on the diet. That's a before and after. So we might be testing a diet there to see if the diet has had any impact. And what we might do is take one set of samples before and then one set of samples after on the same people. On the same person, we'll take two readings. There's a before and after. Alternatively, we might have one group getting a treatment and the other group having a control. Once again, it could be the same person. For 1 week you give the treatment and then you let that wear off, and then the next week you give them a control treatment or something like that. Or you might have a group of patients, 50 patients get the treatment, another separate group, 50 patients get the control, and that's a treatment and control situation. Or you could have two groups, just any two groups. You could have a situation where you have male, female, young, old. Now, generically, what we want to do in this exercise is we want to compare the means of the one group to the mean of the other, and the way we're going to do a comparison is by taking the difference. So our null hypothesis here is going to be some difference equal to, let's call it delta. Look at the difference between the two means and call that delta, and we're going to hypothesize something about delta. Now, the most common hypothesis is that delta is equal to 0. So the most common is that there's no effect. So the diet, for example, has had no effect. Or the treatment, this new treatment that we're looking at, the null hypothesis might be that the new treatment has had no effect. If we can reject that hypothesis, then we'll say, oh, good, look, the treatment has had an effect. But this is the way we can set it up for the two-sample situation. Now, what do we do? Well, as before, we're going to determine our statistic. So our statistic is going to be, look at the difference between the two sample means, just like before. Before we looked at the difference between the sample mean and the population mean. Now we look at the difference between the two sample means to make some statement about the two population means. And so subtract the hypothesized value. So for example, if that's 0, then we wouldn't have anything there. And then, just like before, we're going to divide this thing by a standard deviation of some sort. I've put t here, jumping the gun, assuming we don't know sigma. But if we know sigma, we could create a z there just as easily. But I'm just going to talk about the situation when we don't know sigma. Now, the whole trick is going to be, what do we put in there for the standard deviation? That's the whole question. What standard deviation to use? And so far, the theory that has been worked out, and this is what we're going to talk about now, requires us first answering this question. Are the two samples independent? If they aren't, for example, if we have a before and after situation where we're taking the measurements on the same person, or we're looking at the right eye of a rat and the left eye of the rat, they're not independent, they're on the same rat, then we'll say the answer to this question is no. And we're going to do one set of calculations for that. On the other hand, if the sample is yes, namely that they're independent, so we're talking about different people. Maybe we're doing male versus female. Maybe we're doing young versus old. Maybe we break up the population into two groups. One group gets one treatment and the other group gets the control treatment. Something like that. When, for example, we're dealing with different people, then we would work with the independent situation. Okay? So we're going to attack these one by one, first in the dependent situation and then in the independent situation. Okay, so let's take a look and visit our data set. And here are the variables. And let's see if we can think of some hypotheses or some investigations we may wish to do where the two tests, where the two samples, rather, would be dependent. So for example, let's scroll down here. Here we go. We know here there's the systolic blood pressure, 1. Well, there's also systolic blood pressure 2. So we might want to know whether there's a difference in systolic blood pressure at time 1, at visit 1, and systolic blood pressure at visit 2. Or total cholesterol, there it is, cholesterol at time 1, cholesterol at time 2. Those are the kinds of issues that would lend themselves to doing a dependent test. So what do we do with dependent tests? With dependent tests, we reduce it to a one sample test. What we do is we look at the differences between the two. So for example, let's just for argument's sake say we're looking at the total cholesterol. So let's generate a new variable, let's call it tot col, and that's going to be the total tot col at time 2 minus tot col at time 1. So now we are going to see the difference between the cholesterol levels at time 2 and the cholesterol levels at time 1. So we generate that and we look down here and we see, wait a minute, there are going to be 675 missing values generated. So this should be of concern to us because what this is saying is that there are 675 individuals who do not have both cholesterol readings at time 2 and at time 1. And that might very well impact any sort of inference we want to make about the change in cholesterol level, because these 675 who are missing might have a very different story from the ones who are not missing. But let's move on and not worry about that right now. All right, but let's move on So now let's take a look at what this variable looks like. So let's summarize tot chol, and let's see what it gives us. And so the mean is 13. There are 3,759 observations, and the standard deviation is 33. And not everybody shows an increase, so there are some negative numbers, but the average increase is 13 units. So it looks like there is a definite increase in total cholesterol level. Now, let's take a sample of these and let's see what that sample shows us. So let's sample. What should we take a sample of? Let's say 49, just for argument's sake. So 49 count. Okay, now let's summarize total call and let's see what that looks like now. And we see that it's a pretty good estimate. The mean of this is pretty close to the mean of that, to the overall mean. So the mean in the sample is a pretty good estimate of the mean in the population. Now we can test. So we can test the null hypothesis. And so we go up here, classical tests of hypotheses, one sample mean comparison. So remember, this is just like the one sample mean. And the variable we're going to put in here is tot chol. And the hypothesized mean is that that's 0. So let's hypothesize that there's no difference between total cholesterol level at visit 2 and at visit 1. So, okay, let's submit that. And what do we get? We get that, here it is, the total cholesterol, that the confidence interval in the difference in cholesterol levels between visit 2 and visit 1, the 95% confidence interval is somewhere between, is 3.25 to 21.92. So this does not include 0, so we know that the confidence interval approach to testing the null hypothesis, that the difference is 0, would reject that null hypothesis at the 5% level. Okay, now let's look at the hypothesis testing approach. So the null hypothesis is that the mean is 0 and there are 45 degrees of freedom. And if the alternative is that the mean is not 0, so the two-sided alternative, there it is, has a p-value attached to it of 0.0093. So we would reject the null hypothesis here. So in summary, what did we do in the dependent case? What we did is for each individual, we took the difference between the value at time 2 and the value at time 1. So time 1 was the first visit, was the initial visit, and then at time 2 was the next visit. And we did that for the first individual, then we did the same for the second individual, etc. We did it for everyone. And now we don't care about this anymore. We focused our attention on these differences. And then that behaves just like a single sample. With what mean? The mean was delta. Delta is the difference between two means. So now we're back in the single sample situation with n observations based on the n differences. And now we can set up hypotheses about delta. What value is delta? And as I said, the most common one is that delta is equal to 0. So we would do exactly like we did before, calculate the sample mean. So that's the sample mean of the D's. So act as if D's are our observations. Calculate the sample variance of the D's. And then, let me not hide this, then take the mean of the D's, sample mean, and divide by the standard error. And here we have mu of the differences. I slipped in, that should have been a delta. And now this is distributed as a t with n-1 degrees of freedom. And this is exactly what Stata did for us.